We are greatly honored to have Dr. Orit Zaslavsky from Department of Teaching and Learning at NYU to be with us. Orit is a retiree from Technion Israel Institute of Technology in Haifa, Israel, and is now a professor at NYU. So she has served as an associate editor and on the editorial board of JMTE, the Journal of Mathematics Teacher Education. Currently, she is studying the interplay between example, definition, and proved in developing mathematical thinking and conceptual understanding. She's just received an NSF grant to develop and disseminate a new undergrad course in mathematical proof and proving that addresses students' difficulty in understanding proof. It is well recognized in the field that she is specialized in mathematics teacher education and has been among the first scholars to study the development of teacher educators from both theoretical and practical perspectives. And within this broad research area, she has investigated and conceptualized the nature of productive mathematics-related tasks and examples. And today she's going to share her thoughts on there is more to examples than meets the eye, what is entailed in generating and choosing instructional example in mathematics. Please welcome.
Thank you for your kind words and introduction, and I must say I'm very excited to be here. It's my first visit here, although so much influence on the field came from here. I'm embarrassed to say this is my first visit here. So thank you for inviting me, and this is particularly exciting for me because Tom Cooney made special trainings scheduled to come, and this is particularly an honor for me because we just talked about it that 35 years ago, embarrassing to say, when I was really, I didn't even know I would continue to this area. I was a mathematics teacher, just thinking of my master's. It happened to be in Europe. It was the first, right, PME. And I stopped for a day and happened to go into this room where Tom was having a workshop around teacher education, and it was really sort of a milestone in my thinking, in my direction, in this field. So thank you, Tom. And Tom was the one that invited me on board when he just lounged JMTE to be on the editorial board. So I really am very grateful. And okay, so within this field that I find so fascinating, and actually I started, when I reflected on my work as a teacher, I taught 12 years in junior high and secondary mathematics school classrooms. I spent, I think, most of my time as a teacher working on finding examples that could do the work. And I found that it takes a lot of time. It was like a problem-solving situation, and I couldn't really articulate and say, how could I teach other people to do this or so on, but I've been worrying about it. Not that I have any answers now, but I think I have a little bit more to say about it. And before I start, I just want to say three issues that have to do with examples. What is an example? I'm not going to give a definition, but I do want to say that for me, it's not any mathematical object. It's only an object that we look at and we could say this is an example of. Because a particular object could be examples of different things. So in order to look at it at a certain point and say, well, this is an example of a quadratic function, so in a different context, it could be looked at as this is a bunch of symbols, an example of a bunch of symbols put together or whatever. So it's really, in order to examine examples, we need to know at a certain point what this object is an example of, or at least what is it intended to be an example of. So this is sort of narrowing it down a little bit. talking about all topics. Another thing I want to just point to the fact that examples are in the eyes of the beholder. What I may see in an example may not necessarily be what someone else sees in it, so it has a lot of subjective elements. But within this subjectivity, and this I think is something that I'm trying to push, we could say for certain examples, I think we could agree that to a large extent that some examples are likely to be more transparent to the ideas we want them to exemplify than others. And I think that's where we're trying to as a field, think of what would make an example more transparent to this big idea or whatever it's supposed to capture to a larger audience. So this is sort of the big perspective I'm covering. So what am I going to try to address here? First of all, why deal with examples? The fact that I'm fascinated about them is not sufficiently reason to worry about it. What do we know about exemplification in mathematics education? I'd like to look at examples that could, and loving examples, a lot of the ideas that I want to convey I'm going to do through examples. So I'd like to bring examples that convey the complexity and affordances of generating mathematical examples. And then move, and this could be for learners in general, for thinkers, problem solvers, anyone. In particular, as Ron said, I am interested in teacher education, and with this with this lens, I am interested to see how do mathematics teachers choose examples in and for their classroom. And I will try to offer some reflections, and so some added value is to look at some of the things I'm going to present with the question of what learning opportunities are involved or could be involved in dealing with examples. So this is pretty ambitious, and I may not do all, but I'll try. So why deal with examples? First of all, examples are an integral part of mathematics. It's an important component of expert knowledge, and there's a beautiful article of Ruslan Michner, I don't know what it falls under, that really talks about understanding mathematics, and there she really talks about examples of being a very critical element of mathematical knowledge. Examples are fundamental elements of good explanations. There's work in Legere Leinhardt and others that talk about that. The knowledge required for carefully selecting appropriate examples that are useful for highlighting salient mathematical issues is considered critical for mathematics teachers. Examples play a critical role in learning. We have a lot of worked on examples, how people learn from them. Concept image, the whole idea of concept image relies on the examples to which we are exposed to. Foundations of generalization and abstraction build on examples, analogical reasoning, inductive reasoning, and dimensions of possible variation. This is a field that John Mason and Ann Watson work on. We also have some evidence that through examples we could reveal some thinking and what individual conceptions are. Zaslavsky has work on that. And examples play a role in determining the validity of mathematical statements, and what exactly role they play, I will refer to a little further. So what do we know about exemplification in mathematics education? There's often a mismatch, and that has to do a little bit with the what I mentioned before, in the eyes of the beholder, between teacher's intention and what students attend to. When a teacher presents an example, he or she sees its generality and relates to what the example represents. However, a novice learner may notice only particular features of a specific example, paying attention to the example itself, not to what it stands for. In other words, Richard Skem talks about the element of noise in an example. You can't talk about an example that doesn't have irrelevant elements to it because it's specific. And this issue of how to help students or learners attend to what this is really trying to exemplify is a non-trivial issue. Studies related to concept learning suggest that examples and non-examples are a concept of a concept being introduced in a carefully thought way so that the learner distinguishes between critical and non-critical features and constructs a rich and appropriate concept image, or similar to concept image, there is now the notion of example space, to avoid prototypical conception. And and there is some evidence that when you do carefully sequence in this similar way along these ideas, some learning could occur. And this is just a quick collection of examples that Rita Herskovich used for her study in terms of the concept of a height in a triangle. So if you look at height, it has two critical features. It has to go through a vertex, and it has to be perpendicular to the side opposite it. But in every example, there are other things to it, and some are critical, some are not, some, and so on. So if we have just one feature that it goes through the vertex but not perpendicular, it can't be a height. But, for example, it doesn't have to be, but it could be one of the sides. And this is not critical, but possible. And getting a rich idea, so we don't always think of a height as being inside the triangle in a certain position and so on, would only be possible if we expose to a rich collection that's carefully thought through. In terms of example spaces, in the work I did with Irit Pellet, we use the term example space to refer to teachers' personal collections of example-related knowledge that they draw on when they need to come up with an example for a certain purpose. Some difficulties in selecting appropriate examples we were able to attribute to a limited example space that we thought we identified. Ann Watson and John Mason also elaborate, and they have a whole book on learners-generated examples, and they talk a lot about example spaces as collections of examples that fulfill specific function, they're influenced by individual experience and memory, and may not be structured in ways which afford easy access. There's also a lot to say about examples and proof. And there's a tension between empirical and formal aspects of mathematics. We see that as, we could see, there is evidence that is a major source of students' difficulty with proving. Students tend to rely on specific examples as sufficient for determining that a general claim is true. We have what Yoshino calls empirical proof schemes, and we also talk about example-based reasoning, where you draw on examples to reason, and some could be fine and logical and well-grounded, but some inferences may not. And we know that students have difficulty with counterexamples, and sometimes they regard them as exceptions, not as examples that violate or refute a claim. So we have some evidence of those, and within this tension suggests that understanding of the logical relations between examples and statements is non-trivial and critical for proving. However, this kind of understanding is not usually addressed explicitly in school curriculum, and I would also say not even in higher undergraduate mathematics. So this led to a study that I've done with a doctoral student of mine, Oli Buchbinder, in which we addressed the question, what does it mean to understand the status of examples in determining the validity of mathematical statements, and how may this understanding be captured and developed? And as a first stage to even dealing with this, we had to unpack this question, what would this mean, or what are the roles of examples in determining the validity of mathematical statements? So for this, we developed a framework for understanding understanding the status of examples and establishing the validity of mathematical statements. And I will illustrate it with respect to a specific false proposition. When you do it with a proposition that you know is true, it's not as powerful, but it's possible to do. So let's take this statement. In a parallelogram, any, the diagonals are of equal length. Okay? Now this statement, you could say, is never true. I mean, if you think that some parallelograms have equal length diagonals and some don't. This makes this a rich way of illustrating our framework, and here it goes. We look at statements as the domain. A statement has a domain and what it actually states. Okay, so in this case, the domain would be the set of all parallelograms, and the property of statement is having equal length diagonals. Okay, and for this statement, we can think of a universal statement and an existential statement. Okay, so we could ask one. The universal would be all parallelograms have equal length diagonals. And the existential would be there exists a parallelogram with equal length diagonals. And in terms of roles, and this, by the way, this framework took a lot of time to develop, and then we used it in terms of designing the study and then analyzing our results against this. So it's not something that we open the book and just put it off the shelf. So one of the things, and again, it has our thinking, and it may not be universal in that sense, but I think we have captured the big picture. So when you talk about validity, determining validity, sometimes you want to prove something, sometimes you want to disprove it. Okay, so that would be the goal. We have a universal statement, we may want to prove it, we may want to disprove it. It's the same for existential. And then come the types of examples we could find. So for example, we could find a confirming, we call it a confirming example, that actually for it really has equal length diagonals. So what would the status of this example be in determining whether this statement, whether these two statements are true, false, or whatever? So one of the problems we have that this is insufficient, although it's not so clear that students see it as insufficient, particularly if we have a lot of those. Okay? And it is sufficient, however, to prove an existential, the existential. Okay? However, it will not be applicable, will not be helpful or irrelevant in a way for the other cases. So this is part of understanding how examples play a role in this process. We could think of a contradicting, what we call contradicting the universal statement, but it's not a non-conforming non-confirming for the existential. It has a different role with respect to the statement we're looking at. If we take a non-rectangle rhombus, because we could take a rectangle rhombus, which is actually a square, so take a non-square rhombus or a non-rectangular rectangle. So then it would be contradicting the universal one, right? But it will be non-confirming, doesn't contradict the existential. That's also a deep idea here. So it would be sufficient to disprove the universal one. It would be insufficient to disprove the existential one. And for the other parts, again, it's not applicable. It doesn't add any information for us. Then we could think of other. We took all the possibles. If you look at the domain and whether it satisfies or not, so it could be in the domain and satisfy, in the domain not satisfied. It could be not in the domain and satisfy, not in the domain and not satisfied. So we took all possibilities, not that we're just throwing out examples. And so this would really be irrelevant, because if an example is not in the domain, who cares if it does or doesn't have property? Again, not easy for students to agree and understand, but this is a mathematical analysis. So from a mathematical point of view, this is not applicable. And another irrelevant would be that it's not in the domain, but also doesn't have the property that we're talking about, also would be not applicable. So this would be the big framework which we developed when we were really worrying, what does this mean? So this is an example of taking the issue of examples in a particular context of mathematics and asking ourselves, what would we like someone who is graduates from some part of mathematical, whether high school or undergraduate course or whatever, to be able to understand and be able to work with and operate. And this is the framework we came up with. I'm not going to go into the study, but we really asked, what does it mean to understand the status of examples of determining the validity? And we considered the understanding of that, this kind of understanding, as becoming fluent with the logical inferences that can and cannot be made based on the different types of examples with respect to the validity of the two kinds of statements. And Oli's dissertation really deals with this, and I'll just give you an example of what some of you asked me when we met before, how do I come up with tasks and what tests and so on. So after we developed this framework, we were able to say, what would be good research instrument or a good task that could address this kind of understanding. So a generic kind of task was to really determine the validity of different tasks. So one task, this is a collection of tasks, was for each of the following statements, determine whether it is true or false. Explain or prove your answer. This is a generic task. However, it has to do a lot with the specifics, with the examples of the statements that we plug in. Because if it's something very trivial and students know it right away, so they don't bother really reasoning through this kind of framework or similar to this framework. So you really have to think of examples also that are not familiar, that you can't just say, yes, I know it's true, I know it's not. And so we did it similar in algebra and similar, the big generic type of task was similar, the same for algebra and geometry, but the specifics changed. So for example, these are 6 specific statements that we used in our study, which students had to reason through it and say, if n is an even number, then a to the n is always positive for any integer, and so on. So I'm not going to go through it, but this is an example of how a framework leads to a task, and then through this, we analyzed what students did and saw 2 different things. First of all, a lot of how they think about examples came up, but also through doing these tasks, we could see a development of their understanding of all that. So, as I said, I'm not going to the study. This could be a whole presentation, but this is an example of a body of research within this big theme of exemplification. There also, so this comes from a learner, but not just learner perspective. And by the way, the framework I'm talking about, the course on proof and proving that I'm giving now at NYU, I worked with this framework with free service. Actually, some of them are in-service teachers that are working on their masters towards certification. And we devoted a whole classroom period for that, and in the end, some of them came and said, why didn't they show us this in high school? How come we never taught it? And it really, if you think of it, I think you would agree that putting examples in as a topic, not just for teacher preparation, but also for students to think about, to be more explicit and not just do it without calling it names or structuring it or using it. But it's something that's sort of missing, at least in the extent that we should include. So, in addition to this, we have some studies, very scarce, on teachers' choice and treatment of examples. One of the main sources that I could refer to is Tim Rowland. He did a study with elementary teachers, and he found 3 types of novice teachers' poor choices of examples. One had to do with, he called it obscuring the role of the variables. So for example, if you want to teach a coordinate system, and you choose to show how this works for a pair that's 5, 5, this is clearly not helping the student understand how this works. So it's a specific case, it's okay to use, but it's really not doing the work for us. Or he also said using, selecting calculation to illustrate a particular procedure when another procedure would make more sense to do. For example, 49 times 4. If you bring this to show how you multiply the algorithm for multiplication of one-digit number, this doesn't make sense when you could think about it as 50 minus 1, and then you could do it mental calculation would make more sense. So to use this example to show it is like not thinking in a broader sense of what it is we want to do. And he also has examples of where teachers randomly generate examples when really you should think carefully about the specifics. Nonetheless, having said that, and I already mentioned it, many teacher education programs do not explicitly address the issue of judicious choice of examples. It appears to be part of teachers' craft knowledge. Because teachers do, I mean, I could say about myself too, the knowledge I have of examples is to a large extent craft knowledge that I've developed beginning as a teacher and then as a teacher educator. I didn't read about it much. I mean, I tried to, but it didn't really help me much. Our work proposes making a step towards, I'd say, learning from experienced teachers, their strengths and their weaknesses with respect to treatment of examples, as well as how their knowledge of instruction of examples evolves. I draw now on data from 3 sources. Workshops with mathematics educators, not just teachers. They could be some university professors or people that work with teachers, teachers of teachers, classroom observations, videos of mathematical lessons. And I want to try to convey to you the complexity and affordances of generating examples through 3 cases. Not the cases in the common way. 3 examples. Okay? Case 1. Here's an excerpt from a classroom. The teacher says, well, give me a fraction which lies between 1/2 and 3/4. And the pupil says 2/3. Teacher asks, well, how do you know that 2/3 lies between 1/2 and 3/4? People said because the 2 is in between the 1 and the 3, and the 3 is in between the 2 and the 4. How would you deal with that response? Okay? I'm sorry, I mean, I could do a workshop. I do workshops on that, but this is not a workshop, so I have to take away the fun of working on this. And actually, I didn't create it. This is in Alan Bishop's article from 1976, in which he describes his own experience as a mathematics teacher, I think it's a 5th grade or something like that. And someone again, you asked me about where tasks come from. So this thinking, you know, when you have a mindset on task, and right away think, how can I turn this into a task with my teachers? So here's what a group of experienced teachers suggested. I brought that and had a discussion, and then they had to figure out whether this response is correct or not. And they started trying different kinds of examples. He says, oh, it seems to work. They tried another one. Yeah, it seems to work. And this is actually the order in which it came up. And indeed, it does. And right away, remember the framework of examples? If you don't find a counterexample easily, the claim is probably right. Okay, and these are teachers. And teachers that have pretty sound mathematics in terms of formal mathematics. And it's not that I belittle any of their qualities. It's that it's a matter of becoming aware of and thinking of these things. It's not that something that you know, if you know a lot of mathematics, you've already thought of. So then they continued, and this doesn't count, not convincing, could be dismissed or treated as an exception. Remember, we're still talking about it? Because here we have, you know, it doesn't look 2/4, it's not fair, it's really like, it's the same as such. But
No,
So,
3/4.
it's like too special, too different, it doesn't count. Okay. Then this also doesn't count really. It doesn't look, you know, it's like a really special case of 3 of them. And this may be convincing. We need more of these. Okay? And look at, again, you could be correct mathematically, but still you need to get the inner conviction inside you. And then they tried to approach it more systematically. The fact that there was some uncertainty was a trigger to think more deeply about it. And then they came up with more systematic examples, and they were able to say that that doesn't always work. And Alan Bishop says, by the way, just to make it clear, why is this such a good example to me, and why did I quickly grab it and say this is a wonderful opportunity to work with teachers? Because this rule works in certain cases. So it's not as if the student was completely off. You may even have meant it correctly, because if you take the middle, the exact middle between the two nominators and denominators, then it's okay, and you could prove it, and it's really interesting. But if you just take any number in between, then it doesn't necessarily work. So it's a very rich site for really thinking this through. Actually thinking about this particular problem, but also in a broader sense, what are these examples offering us? What could we infer from them? So in that sense. Anyway, but then Alan Bishop writes really, I love what he writes about it. He says, well, as an experienced teacher, Bishop employed a strategy that had worked for him and other teachers in the past, the strategy of buying time. And he says, what I did was pause, smile, repeat the statement at length, writing on the board, call it Jonathan's Law in honor of the people who suggested it, pause, ask the other children, what does anyone else think about this? And pause, and then write on the board a counterexample. Okay? And he himself, he said it took him 20 seconds and so on until he found it. And this really captures another element that I hope to be able to touch on, that has to do with needing to think on your feet. As teachers, a lot of some examples we could have pre-planned, but sometimes we have to really come up with examples in the moment. We could always say, well, we'll think about it and let's go home and come back, and that's okay. But still, we would like to be able to do that also, as I will show later. I think if you see it, you saw in those who read the article I have with Louis Loddy, we talk about the difference between spontaneous examples and pre-planned examples, and there's some case to it. Considering the following claim. Any two rectangles with congruent diagonals are congruent. Okay? We know it's false. Okay? And this is a claim we gave many years ago. Rita and I, Kelly and I, gave it to teachers, both elementary and I think also there was some secondary, when we wanted to see how they generate examples. Because there was not a question whether this is true or not, but the issue of examples came up here. So, and then we made some distinctions about more general or examples that carry more an explanatory power. So in this sense, we could say, here's an example of a more generic or explanatory example where we say, okay, here's a way of generating a lot of different rectangles around the same diagonal. And we can justify it and show why there's an infinite number and so on. So we called it sort of a generic. But recently I went back to the data we had. This was like 96 or 7, I can't remember. And I looked at the examples teachers offered. And this was an example that sort of this or similar one came repeatedly. And I was wondering, because rethinking, and this is part of what I think is exciting, the spiral nature of our thinking about things that we worry about for a long time. I said, it doesn't make sense to give an example of two rectangles with giving just one side. How come they took one side and the diagonal? You know, I would expect to give two rectangles and then so on. And I wanted to, so I dug a little further into this, more deeper. But before that, I just want to point to this, for example, just providing these two sort of examples, it still doesn't say this is a counterexample. Because for that, we would need to do more. We would have to make sure, first of all, that it's possible. These are two possible rectangles with these dimensions, so that's easy to show. But we'd also have to make sure that in this case, this side isn't 4. Because if this is 4, and this may be 2, so it's actually not two distinct rectangles. So this has, even when you suggest an example or counterexample, you have to show that it's a correct example, correct in the sense that it really is an example of what you claim it is, and that it exists, and so on. So even in this little thing, there are missing elements and so on. But then I said, okay, so let's take this further and say, what if these examples were not helpful to your students? And suppose you wanted, and I'm not arguing now with whether this is a good pedagogical move or not, but this is a possible pedagogical move to say, well, suppose you wanted to offer a hands-on activity for your students to construct two different rectangles on a grid paper and to measure and see that, oh, these are two different rectangles that have the same length of diagonals. And to accurately construct a rectangle on a grid paper, we would want it to be integral measures for purpose of accuracy, not because we can't put fractions, but just for this. So this is sort of the problem situation that I pose, not just to teachers, but to math educators. What example would you use for this purpose? Okay? And I'll spare you the time to work on it. To find such an example, you need to find two distinct pairs of integers that satisfy the following conditions. You want the sum of the squares of the two to be equal to the sum of the squares of the other two. This is not an easy problem. So if you want as a teacher, let's say elementary teacher, to think in advance and say, why don't you this group do a rectangle with a 3 and a 5, and this with a 6 and a 2, and measure, and let's see what happens. This is not easy to come up with. And responses from prominent mathematics educators and researchers. I won't go over everything, but one second. I recall that a prime number is the sum of two squares, and if and only if, and this whole thing. Okay, I'm not going to. Someone else says, I asked a local number theorist. He sent me an email after my workshop. It still bothered him. And okay? And then someone else at a workshop that I did in Siena, we had a group of scholars, 20 scholars meeting to think about the simplification. So one of the ideas was, here, let's start doing a plot and filling this in and look where we get the same numbers. Okay. Fascinating. Okay. And here more. So we have a lot of examples. And from here, we can even think of here. This could be something that we could give students. Some would do 1 and a 12, and 1 an 8 and a 9, and then they could measure the diagonals and see. I mean, they will see that it's the same. They won't really be able to say how. Square of 145, we don't expect them to calculate it at this point, but we could really do an activity. But again, I want to remind you that this is part of the complexities and affordances of limited examples. This could have a serious demand on teachers. Case 3. John Macy talks a lot about the affordance of the generic type of task that says, give me an example, and another one, and another one, and another one, and then push students or learners or scholars to think more deeply about these concepts. So I try to do this with teachers, in-service teachers in secondary school. They teach advanced mathematics in secondary schools in like 11th and 10th and 12th grade. And I chose to ask them about, I do more, but I'm presenting here, but I chose to do with periodic function. And the first three examples that came up were easy. Sine of x, cosine x, cosine x. And then someone said a combination would also be good. Great. So we could have said, good, let's move to another constant. But we didn't. And then the fourth example took longer. And Ruthie said, maybe we need a geometric series, something that isn't continuous, something discrete as y. I want a function and I want a series, like a collection of points. And why do you feel you need something non-continuous? A series isn't continuous, okay. We know we can treat a series as a function, but where does periodicity come to play? We can take this series like, suddenly someone helps her and says, oh, minus 1, 1, minus 1, 1. They didn't think of that before, but this, if you think of a series as a function. Jacob, as I said earlier, since it is endless, it's like sine. This is something they've never thought of before, the connection between this and that. Okay, so how do we know it's periodic? What is its period? We first have to find its rule, and so on. It's actually so-and-so. It's not, controversy. And then some say different things. So just to note, this example was generated collaboratively and took much longer than the first three. As they were trying to construct a different example, their example space expanded to include not just trigonometric functions, which they had first had in mind. Once they opened to this idea, the next three examples came more easily. It was like something, oh, we thought a little out of our comfort zone, and now we suddenly have a bigger collection. So actually, if we look at these different series and time that took in terms of seconds, so you really see that this here was a big step, and then it goes again, and then when suddenly, once you find another one, you say, oh, now I can do some variation on it. So it's like grouped together in a similar type. But this activity really, by just asking them, not telling them, asking them to give another example, some prompts, they really got to better understand the notion of periodicity with respect to functions. So if we're talking about the affordance of these kinds of examples, I think this shows how this kind of task could really allow for any group to deepen their understanding of broad. Just to note that another type that was missing was this kind of. And we could have gone further and so on, but we didn't. So it's not as if now they completed it all, but they extended it. Okay. And here, okay, we go on, and I think I'll just go on. So we could go. Okay, now the next question. How do mathematics teachers choose examples in and for their classrooms? This has to do with, I think some of you read the paper I've done with Louis Zodit and Omar Levy. Actually, Omar did a different aspect, but we had a grant from what is parallel to NSF, it's ISF, Israel Science Foundation. And I draw a little bit about some data I had from visiting at UCSD. And just to say the goals, we wanted to try and characterize experienced secondary teachers' ways of selecting and treating examples in classrooms, to investigate their underlying considerations involved in their choices. This is really seeing what they developed on their own, to identify opportunities or situations for which treatment of examples facilitates teachers' learning. Okay, we weren't looking at this part on students, we have another part that does. So what we did, we randomly and carefully selected classrooms from experienced teachers. It's sort of the methodology of taking the best case and saying, okay, let's go to teachers that we think could do the best for different reasons, different criteria, whatever, and see what goes on there. And then if everything's great there, then we could go on, but let's see, if if they have some difficulties, we could suggest that it would be not just for them. We have pre and post lesson interviews, documents of lesson plans, worksheets, research journal, and teacher workshops. And we looked at examples with respect to concepts, to statements, we mentioned, and to processes. And one of the things we looked at, as I mentioned before, at pre-planned and spontaneously generated examples. And one of the pre-planned examples, just to capture and see what an example, a pre-planned example, try to look at the characteristics, is this is a sequence of examples that a teacher prepared in order to teach how to, given that we know how to find the area of a rectangle, how we would find an area of a triangle. So this was the first, the rectangle, then it moved to the second one, and then to the third. So as you see, this is a special case of a triangle, and the third appears to be a generic case, or at least more generic. And the teacher goes and says, okay, here's the 3 And I'm not talking about exactly what the students are. This is a sort of a short account of a lesson that with the students and teachers, the students came to the board and so on. But I'm looking more at the elements. So then she reminded them it's length times width. And then here, they completed it to a rectangle and were able to say, oh, so in this case it has to be half of this. Okay, so this is already getting to a specific triangle, but not a general. And now here, so these are tied, and then comes the other one that's a further step. So if you see in terms of gradual difficulty or development of the idea, she has it here, and these are linked a little differently. They are, it's like 2 parts of the same, like these are concerned. And then she's, okay, wait a second. And at this point she says, okay, can I split up the 6? She meant, I mean, definitely split, but she talks about numbers. The student says, yes. Okay, I can split it up. Okay, how do you want me to do it? 3 and 3, 1 and 5. So the student says 4 and 2. So the teacher says, okay, so obviously you would think this 2 and this 4, I'll go in a second, but what I want to point that this looks very, could seem as just nothing specific, nothing so special, but if you look at it deeply, it could be interpreted in conveying the general aspect, the random. Remember I said Tom Roland found that elementary teachers used randomly selected examples in inappropriate ways. But here, saying it could be either 1 of 5 or 3 or 3 or 2 and 4 says really that it doesn't really matter where this point is. Not explicitly, but this is giving the nature. So it's not this specific place where we put it. And you could choose anything you want to do the following. So what do I have to do here? That's what you want to do, right? And then she continues and she says, okay, so if this is the 2 and this is the 4, we have this part, we know already how to do it. We have this part, we know how to do it. And we get 3 plus 6, and it's 9, and we really get the same as before. And the question is, and she doesn't elaborate it enough maybe, but she does have the ingredients to do a little bit more about it, and really you have a structure here as how the specifics becomes transparent, or could become transparent to the more general case, and with including the reason. So like if I would talk about missed opportunities, it would be really nice to have them do what would happen if you actually work 1 and 5, and let's see what if it were 2 and a half and 3 and a half, and so on. But she doesn't do it that far, but you could see already the beginning of something that could lead to that. A question could be, well, does it make sense to take 3 and 6 because this has a special relationship between 3 and 6? Maybe, and since we have half, maybe students could think that this has to do with a half. So again, it's hard to think of all the elements, but this is something to think about. So then, and actually to reinforce what I said before, the teacher says, can everyone see what he's doing? He's split it up into 2, this rectangular, and this one here. he says, well, I'm just going to split it by myself and call this 2 and this 4. Call this. It's really like saying, okay, this is like a variable and like a placeholder that now I'm going to say it's like a plug in a for example. So this is a pre-planned, an example of a pre-planned example case of a pre-planned example where the teacher follows through and she interacts with the students and so on, which is pretty, conveys a lot of wisdom, practice. By the way, wisdom and practice and craft knowledge are 2 terms that go hand in hand. Then there's a spontaneous use of counterexamples. In the geometry, these are examples that I'm showing. So a teacher wants to talk about a definition of a medium, and this is what he or she draws and does this, okay? And then a student says, oh, so if it bisects the side, it must also bisect the angle, right? And this has to do with all the visual entailments we have with visual examples. Okay, to what extent can we rely on it or not, and so on. On the one hand, we don't want to be able to rely on it. On the other hand, this is very, very salient, very hard to ignore. So we don't want to have examples that are totally misleading in a way. So following this, the teacher immediately thought of a different example that will not have the student have this image. So this would be a spontaneous example that the teacher came up with as a response to what a student brought. I mentioned before also, but one of the interesting things we found that it's not so clear. I mean, the cases where examples are incorrect in the sense, in a number of senses. So we found 3 types of incorrectness of mathematical example. One had to do with the fact whether it really satisfies the necessary conditions to qualify such example. For instance, treating the absolute value function as an example of an everywhere differential function would be considered incorrect. Or maintaining that 0.333 and so on is an example of an irrational number is also incorrect. And some teachers actually brought this as an example of an irrational number in a workshop we worked with. Okay, a repeated decimal seemed to some of them. So this, again, first of all, shows about how examples could be incorrect. In a way, you could say example incorrect. And also, it immediately gives you an idea of what this teacher is thinking about in terms of a more diagnostic. Treating an example as a counterexample for a particular claim when it does not logically contradict the claim. For example, if you look at, and this is all examples that we found, the functions x to the 3rd plus 1 was brought as a counterexample to the claim that any odd function is monotonic. Okay? So again, so you have to be careful when you look at examples first, and that's what we really did. We first looked whether the example is correct, and then we continued analyzing those that were correct. And sometimes we found that you talk about examples that don't exist. It's easy to sketch something and say, okay, but it doesn't necessarily exist. For example, this type of triangle does not exist. And this was an example we found, okay? So, okay. We have other non-examples. Now, for example, this is a triangle that was in the textbook. And only when we analyzed it, we realized this also is an incorrect example. It does not exist, but it's harder to see, and you don't expect teachers to see it. Because if you continue, this is really 6, and this cannot be larger than 5. 5, okay, 6 cannot be larger than 5. But this is not always easy to see that an example is not existent. So again, the same complexity and what this entails is far from being true. So I think I will not go into the actual findings because, first of all, it's all in the paper. I mentioned the ESM paper, I think it's from 2008. And I will not do that. I just wanted to say that what we did find that teachers had their wisdom of practice in terms of principles, ways of generating examples, and some use the rule from simple, to start with a simple familiar case, More of the spontaneous examples were of this nature than pre-planned. Students' errors, build on students' errors. Here again, when we found an error, we immediately addressed it. So this also is more the spontaneous. Notice relevant features. Wasn't that much different, but still. Choosing at random was always spontaneous. Uncommon cases that you have to think a little more deeply was mostly in the planned. And then there was another case where you say, let's work to the minimum. For example, if you do a long division, it's better to take something with like repeating 7 digits and not 12 or whatever. So there's also say you want the example to be more manageable, require less work, so we could convey the big idea. Some reflections. The work sheds light on critical aspects of mathematics teacher practice that is strongly connected to teachers' mathematical knowledge, pedagogical knowledge, and knowledge of students. And I'm not using, I mean, you could translate it to the framework now of Ball and Hill and whatever. I mean, the mathematics teaching, mathematics knowledge for teaching. I mean, they have the same basic ingredients, maybe a little more detailed, but it really touches on these basics. It captured, what we also managed to capture moments of teacher learning and suggest the mechanism that accounts for teachers' craft knowledge. And one of the really main things, I will claim, but not less important, that I think we could provide a rich, based on all of these studies and the experiences we have and probably others, we could come up with a rich collection of practice-based situations for teacher education programs.
I have time for questions.
If I could ask a question. I was just curious about this mechanism that you talked about at the end. If you could.
Yeah, I was afraid I won't have time to actually go, and it does appear in the paper, but I'll try to. This is a conceptual framework, but it doesn't capture everything. But I think this is sort of what happens. If you look at the concept of a kite, so here's an example. The kite is a quadrilateral. This is a definition. That is constructed by 2 isosceles triangles with a common base. Okay, so this is an example. And the teacher planned to give a non-example. She knows it's important to also give a non-example. And her consideration was for students to notice critical features of examples. So you could say really the teacher builds on her knowledge and resources, their textbooks, her example space, and then and she has a lesson planning. And these all interact, and she has pre-planned examples. And her pre-planned example was this. This she said, okay, now she's going to bring an example why it's important that this base is the base of the 2 triangles. Because here, it's the base of this triangle, but it's the side, not the base of this triangle. Okay, so she really thought of a very nice non-example that helps really draw attention to students why this would be a kite and this would not be a kite. Okay? That's a pre-planned example, a pre-planned non-example. Okay? And then she actually tries it out in the classroom. And she says, okay, let's see why it's important to require that they have a common base. And this is what she brings. Okay? Common base. And here it's not a common base, it's a common something, but not base. It's not base. So she does that, and then she interacts with students. And the student says, but this is still a kite. You drew by mistake an equilateral triangle. Okay? Didn't you pay attention to that? Okay? And even if it's not exactly equilateral, it appears to be. And this is what counts and have students look at this example. They're not going to say to themselves, well, it looks like an equilateral, but it really isn't. So immediately that led to her need to, so this is, we're talking about how craft knowledge develops. So this is an example, but I think we could take it to a more general taste and say, okay, she realizes, oh, I didn't mean that. She has to think on her feet. And sometimes it's not easy to take and go back, but she said, okay, this requires in the moment. Okay, we have a classroom event, interactions between teachers and students, and then in the moment action. And here she sketches another case. It takes her time, but she does it. Another strategy could be to have open it to students. I mean, I'm not talking about how we manage the classroom, but I'm talking in terms of the specific mathematics. Here's her second example. Look how different. Okay? And this really serves her purpose. And she only thought of it as a result of the interaction with the student. She didn't even think that she has to pay close attention of how she constructs. She said, okay, I'll just mark it here and here, big deal. Okay, she had it. And then, now they don't have a common base, and it's not tight. Okay? So, so this is really, if you want, the framework that came out of this study in terms of trying to see some sort of a mechanism where how this learning practice occurs with respect to examples. I think we could probably say that many other moments where teachers learn from their experience could have similar ingredients. Thank you for your question. We didn't plan it.
Any more questions? Maybe one more.
One thing you mentioned that resonated with the experience that I had in another project, and that is this idea of randomly generated examples are not always the best for actually helping students come to construct a concept that you're trying to provide examples for. And I think that's what I found is that's a basic problem with most of the computer systems that provide randomly generated examples, is that there's no thoughtful progression that would help the students actually understand what this is an example of.
Well, I think my colleague Zaslavsky has thought of it in terms of computers very carefully, because you could program, I'm not a computer person, but I think you could monitor some of the conditions of examples that aren't being made transparent to the user, but to monitor that, for example, for the beginning of a coordinate system, you don't bring the 5 and 5 as an example of the point. Or that would be one issue, one answer. I would suggest another suggestion is thinking out loud. I'm in the moment on my feet. I think when you do a lot of examples, like over time, and you expose those that such a variety in which some are this 5-5 and some are different, so it's fine. The problem is that a teacher often does just 1-2 examples as goes on, so then the weight it has may be stronger than when you have a lot of them. And I think in the environments that you're talking, I would suspect that they have an opportunity to encounter so many examples, so randomness may not be an obstacle. It would have to also have to do with what the goals are. What is the concept you want to learn? But I think so that's why I really appreciate Zaslavsky's work, because she's done hand in hand in the development of the software that she's working with, a very deep analysis of the mathematics. So then the program is set to reflect that.
Yes.
And I think she really has a nice article that deals with examples in that sense.
I think we're out of time. All right, thank you.